LangGraph's runtime orchestrates actor-channel interactions through the Pregel algorithm, employing a bulk-synchronous parallel model where actors process channel data in discrete steps. This implementation demonstrates how custom reducers aggregate data across multiple nodes, with channel updates remaining invisible until the subsequent step. We'll examine a two-node configuration where each node subscribes to specific channels, performs transformations, and writes to output channels, with a custom reducer handling string concatenation in the aggregation channel. The setup will reveal how BinaryOperatorAggregate combines updates from multiple sources while maintaining stepwise execution boundaries.
From LangGraph, channels import ephemeral value, BinaryOperatorAggregate. From LangGraph, Pregel import Pregel node builder. Node 1. Node builder, subscribe only A. $x, x plus x. Write to B, C. Node 2. Node builder, subscribe only B. $x, x plus x. Write to C. Def reducer current, update. If current, return current plus update. LC, return update. App equals Pregel. Nodes node 1, node 2, node 2. Channels equals A, ephemeral value ester. B, ephemeral value ester. C, binary operator aggregatester. Operator equals reducer. Input channels equals A. Output channels equals C. App invoke A. Foo.
This example demonstrates how LangGraph's Pregel framework handles data aggregation across multiple nodes using custom reducers. The pattern shows two nodes processing data in sequence, with their outputs converging on a shared channel that uses a custom aggregation function. The architecture uses ephemeral value channels for transient data, A and B, and a binary operator aggregate channel C that accumulates results using the custom reducer function. Node 1 subscribes to input channel, A doubles its value and writes to both B and C. Node 2 then subscribes to B, doubles that value, and writes only to C. The reducer concatenates updates with a separator, showing how to maintain state across node executions. This approach is useful when you need to combine outputs from multiple processing steps into a single result, particularly when the aggregation logic is non-trivial. The trade-off is that custom reducers add complexity compared to built-in aggregations, but they provide flexibility for domain-specific logic. The Pregel runtime handles the execution order automatically, ensuring Node 2 only runs after Node 1 updates channel B. Let's break it down.
From LangGraph, channels import ephemeral value, binary operator aggregate.
Imports two channel-related classes from LangGraph. Ephemeral value for temporary channel values that don't persist between steps, and binary operator aggregate for combining channel updates using binary operations.
From LangGraph, Pregel import Pregel node builder.
Imports the Pregel class and node builder class from the LangGraph Pregel module, providing the core runtime management for LangGraph applications and the builder for creating nodes in the graph.
Node builder, subscribe only A.
Creates a node builder instance configured to only subscribe to channel A. This means the node will only be triggered when updates occur on channel A during the Pregel execution cycle.
$x, x plus x.
Applies a lambda function that takes an input x and returns the sum of x with itself, effectively doubling the input value. This operation is chained using the do method, which executes the transformation on the data flowing through the channel or pipeline.
Write to B, C.
Writes data from channel B to channel C in the current step of the Pregel execution. This operation schedules the value from channel B to be transferred to channel C during the update phase, making it available to actors subscribed to C in subsequent steps. The actual transfer occurs after all actors in the current step complete execution.
Node Builder, subscribe only B.
Creates a Node Builder instance and configures it to only subscribe to channel B. This means the resulting node will exclusively receive updates from channel B and won't process messages from any other channels. The subscribe-only method restricts the node's input to the specified channel, effectively filtering its message consumption.
Write to C.
Writes data to channel C in the current Pregel execution step. This operation queues the data for the channel update phase, making it available to actors subscribed to this channel in subsequent steps. The write itself doesn't immediately trigger any actor execution, but marks the channel for updates when the current step completes.
Def reducer current update.
Defines a function named reducer that takes two parameters, current and update. This function signature suggests it will be used to process updates to channel values in LangGraph's Pregel model, where current represents the existing channel value and update contains the new data to be applied. The function body isn't shown here, but the signature alone indicates this is the standard pattern for channel update functions in LangGraph applications.
If current, return current plus update.
Concatenates the current value with the update value, separated by a pipe character and spaces. If current is truthy, it returns the combined string. Otherwise, the expression would evaluate to just update, though that case isn't shown here. This appears to be a simple string joining operation where existing content is preserved and new content is appended with a clear delimiter.
Return update.
Returns the value of the update variable from the current scope. This line serves as the exit point of a function or method, passing the computed or retrieved update value back to the caller. The specific content and type of update depend on the surrounding context not visible in this single line.
App equals Pregel.
Creates a Pregel instance that will manage the runtime execution of a LangGraph application. This instance will coordinate actors and channels, organizing their execution into steps following the bulk-synchronous parallel model. The variable app now holds this runtime manager, ready to be configured with specific actors and channels.
Nodes node 1, node 2, node 2.
Creates a dictionary mapping node identifiers to node objects, where node 1 maps to the node 1 object and node 2 maps to the node 2 object. This establishes a collection of nodes that can be referenced by their string keys in a LangGraph application.
Ephemeral value ester.
Declares a channel named with an ephemeral value wrapper around a string type. This creates a temporary channel that holds string values but doesn't persist them between graph executions. The channel will only maintain its value during the current Pregel step and be discarded afterward.
B. Ephemeral value ester.
Declares a channel named B with an ephemeral string value type. The ephemeral value ester indicates this channel stores temporary string data that doesn't persist between graph executions, typically used for intermediate computation results that are only needed during the current run.
C. BinaryOperatorAggregate. Operator equals reducer.
Creates a channel named C that aggregates string values using a binary operator reducer. The channel will apply the specified reducer function to combine multiple string updates into a single stored value.
Input channels equals A.
specifies that the actor or component will receive input from a channel named a. This parameter defines the input channels the actor subscribes to, allowing it to read data from channel A during execution.
Output channels equals C.
Specifies that the output channel named C will be used to communicate data between actors in the LangGraph application. This parameter defines which channel receives the output from the current operation, making it available for other actors to consume in subsequent steps of the Pregel execution model.
App invoke foo
invokes the LangGraph application with a single input dictionary containing the key mapped to the value foo. This triggers the graph execution with the provided input data, following the Pregel runtime's bulk-synchronous parallel processing model to coordinate actor execution and channel updates. This implementation showcases LangGraph's Pregel runtime orchestrating a two-node pipeline with custom aggregation. The key pattern here is sequential processing with convergent output. Node 1 transforms input from channel A, writes to both B and C, then Node 2 processes B and writes to C. The critical insight is how the custom reducer in channel C maintains stepwise boundaries while combining outputs from both nodes. Using ephemeral value for intermediate channels A and B ensures they don't persist between steps, while BinaryOperatorAggregate on channel C handles the string concatenation with separators. The trade-off becomes clear. Custom reducers provide domain-specific aggregation logic, but add complexity compared to built-in operations. The Pregel runtime automatically manages execution order, ensuring Node 2 only runs after Node 1 updates channel B, all while keeping channel updates invisible until the next step. This demonstrates how LangGraph's bulk-synchronous parallel model handles both sequential processing and convergent aggregation in a single coherent flow.
The reducer doubles foo into echoes, yet the channel insists it hears only silence.